Hi, boys and girls. This is the video for Lesson 1-5, Equations of Proportional Relationships. This begins on page 41 in your workbook. This is the last representation of proportional relationships that we're going to be learning about. Chapter 1 has been all about proportions. We have seen word problems where they say, oh, so-and-so can text 2 text messages in 1 minute and the other person can do 4 text messages in 2 minutes. Are those rates proportional? And then you would reduce them to lowest terms. If they were the same fraction, you would say, yes, they are. Then we gave you tables of values and we said, okay, these values in this table, this XY table, are they proportional? And you wrote them as fractions, reduced them, and if they were all equal to each other, you said, yes, it's proportional. Then last week, we looked at graphs of lines, and remember the lines had to pass through 0, 0, and had to make a straight line, and that made them proportional. Well, the last thing we're going to be doing in this section is writing equations to represent proportional relationships. All right, and this is what it's going to look like. Here it says 2 quantities are proportional. You know that already if the ratios comparing them are equivalent. The ratio is called the constant of proportionality. Proportional relationships can be represented by an equation in the form y equals kx, where k is the constant of proportionality. So here they're going to write the equation. All proportional equations are the same format. They're all y equals some number and then an x. Now they indicate the sum number with a k. All right, it's the same thing. It's just a little scarier when they substitute it with the letter. Okay, they're saying some number is going to be here, and that is our constant of proportionality. And there is one rule: it cannot be 0. And we're going to talk about that a little bit later in the practice problems. Here they've given you an equation, y equals 3x. All right, and then they've graphed it. Does pass through the origin. And for every one you go right, you go up 3. Go 1 right, up 3. This makes a straight line that passes through the origin, so it's proportional. All right, and this matches this equation because the 3 says that x is being multiplied by 3 every time. Okay, so every time you do x is 1, you multiply that times 3. And you go 3. Okay, so that's just notes and information there. Nothing that you have to write. Okay, example 1, they're going to give you an equation and ask you to identify the constant of proportionality. Remember that all the equations are y equals some number times x, and this is your constant of proportionality. So here it says Olivia bought 6 containers of yogurt for $7.68. The equation y equals 1.28x can be used to represent the situation. So what's the constant of proportionality? It's always the number in front of the x, okay? So the constant of proportionality is 128. What does that represent? It represents the cost of 1 container of yogurt, okay? It's a unit rate, $1.28 for 1, whereas up here we had $7.68 for 6. The constant of proportionality has the same value as the unit rate, which tells us that 1 thing of yogurt costs $1.28. Here we have an example where an airplane is traveling 780 miles in 4 hours. The equation, and again, they're giving you the equation, so they're making it easy on you, models the situation. What is the constant of proportionality? It's always the number in front of the x, so 195. What does the constant of proportionality represent in the context? Well, you read through these, and an airplane travels 390 miles per hour. That's not what it says. It wants to know what's the meaning of the 195. The only one of these sentences that even has the 195 in it is the last one. An airplane travels 195 miles per hour. Well, that's what this would be. It's a unit rate, 195 miles in 1 hour. So D was your correct choice. This is a little blip here where they're showing you, they're trying to convince you that K has been derived, that they really found out that K was equal to this unit rate. Do you remember when we were looking at graphs of lines? And I would tell you, pick any point on the line and write it as an XY coordinate. And then we took y and put it on top, and we put x on the bottom. And when we reduced this so that x was a 1, that was our unit rate, aka constant of proportionality. Okay, that's what they're just trying to show you, how this equation backs this up. Okay, this is your unit rate. It's equal to k. K stands for constant of proportionality. I guess C must have been taken, so they decided to go with K for that. Okay, example 2. Now you're going to have to find your own constant of proportionality. Well, they did it for you because it's an example, but this is the section where you will be doing that. JC bought 8 gallons of gas for $31.12. Write an equation relating the total cost Y to the number of gallons of gas X if it's a proportional relationship. Find the constant of proportionality between cost and gallons. So they've got cost over gallons. They've got the 3112 being divided by the 8 gallons. Then what they did was they divided top and bottom by the bottom number. That's how we get a unit rate. And we arrive at 389 for 1 gallon. So it's 389 for 1 gallon. The constant of proportionality is 389. And write the equation. It would be y equals 389 x. But they wrote it for you there. A mechanic charges $270 for 5 hours of work on a car. Write an equation that compares the total cost to the number of hours. Okay, so we're going to do cost over hours. Okay, he's charging $270 for 5 hours. Well, we always need our unit rate, so we always divide the top and bottom by the bottom number. 270 divided by 5 just happens to be 54. This is the 7th time I've taught this lesson now. And 5 divided by 5 is 1. So what does 54 tell us? It tells us that he's charging $54 for 1 hour of work, right? So write an equation. That's what they want. They want an equation that represents the situation. Well, $54 is your constant of proportionality, so you write 54 here and then x. All right? It's always y equals the constant of proportionality, x. And that would be your answer to that problem. Okay, example 3. They're really complicating perimeter here. I know we all know perimeter is just the 4 sides added together, but they're going to make us write an equation for it and then use the equation to find perimeter. It says the perimeter of a square is proportional to the length of one side. A square with 10-inch sides has a perimeter of 40 inches. Write an equation relating the perimeter to the side length. Well, we've got it set up down here. The perimeter is 40 inches. The side length is 10. Now remember, to get a unit rate, we have to divide the top and bottom by the bottom number. What is 40 divided by 10? It's 4. Okay? So our constant of proportionality is 4. And the equation, they wrote it for you, y equals 4x. Now they're saying, use the equation to find the perimeter of a square with a side length of 6 inches. So they're saying, when x is 6, what's y? Well, we go ahead and we take the x out and we put 6 in. Now you'll notice I wrote it like this so that I'm multiplying 4 and 6 together. 4x is 4 times whatever number x is. 4 times 6 is 24. Okay. So we would have 24 would be the perimeter on a square that had 6, is it inches? Yeah, 6 inches sides. The perimeter is 24 inches. Okay. So they're really complicating perimeter, but there you have it. Now we have Jack in charge of the 120,000-gallon community swimming pool. Each spring, he drains the pool in order to clean it. When he's finished, he refills the pool with fresh water. Jack can fill the pool with 500 gallons of water in 5 minutes. Write an equation that represents the relationship between the total number of gallons, y, and the number of minutes spent filling, x. So they want y over x, or in this case, gallons over minutes. Okay. Well, we don't need this 120,000 thing just yet. We do need this rate, this 500 gallons in 5 minutes. So we're going to put 500 gallons here and 5 minutes here. To turn this into a unit rate, we need to divide the top and the bottom by the bottom number. And 500 divided by 5 is 100. 5 divided by 5 is 1. 100 over 1 what? This is 100 gallons in 1 minute. Okay. So they want us to write the equation. Our constant of proportionality is 100, so we write y equals 100x. So how long will it take to become completely filled? Now we need this 120,000 number. We know it holds 120,000 gallons. And we want to know how many 100 gallons is that, because each 100 gallons is another minute. Well, there's a little trick you can do dividing like this. You can cancel that 0 and cancel that 0. And what's left is your answer here. So 1,200 minutes. But I have to think, if Jack's boss were to say, hey, Jack, tell me how long it's going to take to fill up that pool. And Jack says 1,200 minutes. What's his boss going to say? Exactly. He's going to say, can you tell me how many hours that is? So what we really need to know here is 1,200 minutes is how many hours? Well, how many minutes are in an hour? 60. Right? So if you do the division here, you'll see that it's 20 hours. Which the problem didn't ask for that, but you never know what they're going to ask for on the computer version. So I want to make sure I point that out. Okay. Oh, we have Hugo running. I'll move this little map over here. We don't really need the map, doesn't help us. Hugo can run 4 miles in 25 minutes. How many more miles can Hugo run in 90 minutes than in 25 minutes? Assume the relationship is proportional and runs at a constant rate. Okay, this is tricky. This has multiple steps, okay? First of all, we need to know what our constant of proportionality is so we can solve this problem. And we've got miles per minute. So whenever we're doing speed, we always want to do miles per minute or miles per hour. But in this case, they're giving us minutes. If Hugo can do 4 miles in 25 minutes, well, again, we need to divide the top and bottom by the bottom number. But 4 divided by 25 is a pretty nasty little decimal division problem, right? If we were going to divide, now I'm really going to get rid of this map. If we're going to divide 4 by 25, the first problem we see here is that 25 won't go into 4. So what we normally do then is we add a decimal and a 0. We say, will 25 go into 40? Yes, it will, one time. Put the 1 over the 0 because we had to use it. 1 times 25 is 25. Subtract, we get 15. 25 will not go into 15, so we add another 0 and bring it down. 25 goes into 150 6 times. And 6 times 25 is 150. Subtract, and now we're done. Except, you have to remember that this decimal has to get popped up here into the answer. So, Hugo can run 0.16 miles in 1 minute. That's a pretty good clip. But that's not what the question asks. It wants to know how many more miles can he run in 90 minutes than in 25. Well, we already know how many he can run in 25. What we don't know is how many he can run in 90 minutes. Well, if he can do 0.16 miles in 1 minute, how many can he do in 90? Well, we'll need to multiply 90 times 0.16. Only now we're multiplying with decimals. Well, here's how we do that. 6 times 0 is 0. 6 times 9 is 54. 0 for placeholder. 1 times 0 is 0. And 1 times 9 is 9. We add these two numbers together, and we get 1440. Now, when we multiply with decimals, we ignore the decimal while we're multiplying, but in the end, we have to go back and acknowledge it. There were 2 numbers after the decimal in the problem, So there have to be 2 numbers after the decimal in the answer. So the decimal is going to go right there. So this gives us 14.4, which is how many miles Hugo can run in 90 minutes. But is that what the question asks us? No, it wants to know how many more miles is he running in 90 minutes than he did in 25. Well, he did 4 in 25, and he did 14.4 in 90. So if we subtract the 4 that he did from the 25 minutes, we finally arrive at our answer, 10.4 more miles. Right? And that is the final answer to that problem. It was pretty tricky. It was. All right. I think I have one more. And I think it's just as tricky as the last one. Yep, this is Emily riding her bike. Emily can ride her bike 15 kilometers in 45 minutes. How many more kilometers can she bike in 2 hours than in 45 minutes? Assume the relationship is proportional and she always bikes at the same rate. Well, we're biking kilometers per minute, or are we? Well, the answer is going to have to be in hours context. So let's go ahead and make the jump 2 hours. I think at this point we are all already familiar with what fraction of an hour 45 minutes is. So we want to get our unit rate, or our constant of proportionality. So we know she can do 15 kilometers in 3/4 of an hour. Yes, that's right. 45 minutes is 3/4 of an hour. We want to divide top and bottom by the bottom number to get a unit rate. Be 1 on bottom, but let's look at this. 15 divided by 3/4. To solve this, we first need to make everything a fraction. So we're going to put a 1 under the 15. All right, then we keep, change, divide to multiply, and flip the second number. Now we're ready to multiply it out. 15 times 4 is 60, and 1 times 3 is 3. And 60 divided by 3 is 20. But 20 what? She can do 20 kilometers in 1 hour. This was our unit rate. Okay. So 20 kilometers in 1 hour. So if it asked for an equation, this would be y equals 20x. But it didn't ask for an equation. It wants to know how many more kilometers can she bike in 2 hours than in 45 minutes. Well, we know she can do 15 in 45 minutes. What we don't know is how many she can do in 2 hours. But look at this. If she can do 20 in 1 hour, how much can she do in 2 hours? That's right, 40 in 2 hours. And how much more is 40 than the 15 she did in 45 minutes? 25. So the answer is she can do 25 more kilometers in 2 hours. Oop, pretty tricky. Okay. All right. So that brings me to the end of this section. All right. Stay tuned for the 1-5 practice problem video, which will be coming out next. And if you have any questions, be sure to email me or ask me in class. Have a great day.